Welcome everyone. In this video I'm going to continue the work with the Peltier cooler that I assembled in the previous video. So I have several things on my table right now, and let's start with the cooler just for the sake of simplicity. So this is what I assembled in my previous video. So inside this small structure I have a TEC 12708 Peltier cooler, which is an 8 ampere unit. So I have the cables connected to some banana plugs, so this is how I will connect it to the power supply. And this is the cold side, so I used a big heat sink to have a good contact with the environment. And then this CPU cooler down here is the cooler of the hot side of the Peltier cooler. And what I have now here is just another fan. This will move the air towards the cold side or from the cold side. I haven't yet decided. And then you can see that I have this kind of flexible tube which is used to forward the air from point A to point B. So what I will do here is that I have two different diameters. This is 125 millimeters and this is 100 millimeters, if I remember correctly. So the larger diameter will be used for the hot side because that's much bigger. So as you can see, it covers it nicely. So I will extend it like this and then cut out the outline of the cooler and then pull it around the cooler. So basically it will be like inserted in the hole, and then this fan will run just to pass the air through the fins. But at the end of this tube I will use a high power fan just to suck out more air. And the reason why I don't want to push in the air is because some of these parts will be exposed a little bit, and there will be a hole here which I don't want, or I cannot really separate in an airtight manner. So if, let's say, I put the cooler here, this thing, and this is the inlet and this is the outlet, and I push a lot of air here, then a lot of warm or a lot of air will come out on the holes here. But if I suck the air, so I put the fan on this side, then the air will actually enter into the tube. And of course that will not contribute to the good efficiency or anything. I mean, if you have a hole here, but at least I'm not pushing out the warm air into the environment that I want to cool down. So the large tube will be for the hot side, and for the cold side I will have a smaller diameter tube. So I have to make it a bit oval by just squeezing it, but I will do the same. So I cut out some hole on this which matches the outline of this heatsink, and then I will put this tube on the heatsink, and I will run air through the tube again in the same manner. So I will suck out the air by using a small fan like this. And what I try to see if I can have some, not really an air conditioner, but like a personal air conditioner. Like what I mean by personal air conditioner is that I don't want to cool down the whole room, because that's impossible with this system because it's just too small. But maybe I can drop the temperature of the cold side and therefore the cold air enough that if I, let's say, point this thing with this fan, let's say, at me, then my area at least will be somewhat colder, so I can use this as like a personal air conditioner. So instead of having a fan, like let's say a tabletop fan, which circulates the air in the room, and it is basically just circulating the room temperature air, and the way that you feel colder or cooler is because of the evaporation. But here, actually, you do the same. So you circulate the air in your room or in your environment. So let's say this thing is in front of you at the desk or on the table or next to the bed or something, but it is blowing colder than room temperature air at you. And this is what I will try. So I will try to assemble something with this. Maybe I will use some extra parts just to make it, for example, more rigid, because this is like quite wobbly and flexible and things like that. And then I will do some tests. So let's see if we can make not a room air conditioner, because I said that that's not really possible, but let's say personal air conditioner. All right, so this is the assembled system, and let's discuss all the parts of it. So you can see that I tried to make some hoses out of these flexible tubes. So the system can be separated into two parts, let's say a hot and a cold part. So the hot part is running down here and it is exiting there, pushing the air to another region of this room. And then the cold air is running through this tube. So basically what we have here is that the room temperature air enters here through this fan. So the fan pushes in the hot or warm air, which is at the room temperature. And then the heat sink is here, the cold side heat sink. So hopefully the air will cool down in basically this volume. And then it comes through this pipe or tube. And then we will measure the temperature by this digital thermometer just placed here. And then I put this small electrical tape to have some kind of indication of the airflow. But this will be quite weak airflow, because this is not a big fan, it's just an 8 centimeter small performance regular fan. And then on the hot part, so first of all, we measure the intake temperature here, which is basically the room temperature. And we can say that it's valid for both sides. So both for the cooling air for the hot side and both for the air which we try to cool down with the cold side. This will be the initial temperature. So room temperature air goes in, and then you can see the revealed heat pipes, the copper heat pipes. I was not able to do this thing properly here, but now it doesn't matter for the demonstration. So the air goes in, it will be heated up by the hot side of the Peltier cooler, which is of course cooled by this CPU cooler. And then in between the fins of this CPU cooler we have an 8 centimeter fan, and that is the only thing now which is pushing the air towards that corner of the screen, where this larger exhaust pipe is just getting rid of the air, the hot air. And then we have another thermometer. This is basically the dry bulb thermometer now, and it is showing 25.7 degrees Celsius right now. So this is our initial room temperature, and everywhere we can read 25.7 or 26 degrees Celsius. So that's pretty much the standard. So I start the power supply for the fans, so that is this connection here, and one wire runs here and one wire goes in between the two parts of the CPU cooler. So 12 volts, and you can see the movement of this thing. So there is an airflow. And once again, so the first temperature that is here is going here, so that is the intake temperature. And then the second one will be this thing here, which is the outlet temperature of the cold side. And then the third cable, or the third value on this screen, is inside this pipe here, and it is measuring the outlet temperature of the CPU cooler. So that will be our hot side temperature. Of course not the perfect hot side temperature, but it will give us some sort of indication. And then this guy is the fourth reading, which is basically the room temperature. But in fact, this should give us the same reading as this, because yeah, they are in the same environment. And now I just turned on the power supply, but the power output is not turned on. So we will start with 1 ampere and we will gradually increase it towards the higher values. And I think the final value will be either 5 or 6 amperes. We will see how the temperature changes there. And basically the goal of this experiment is just to see if we can significantly decrease the temperature of the air which is coming out of this pipe. So basically this is the cold pipe. And once again, this is technically not an air conditioner in that sense that it will not be able to cool down the whole room or the whole apartment. But what I'm trying to see is, can we just decrease the temperature by, let's say, 5 degrees here with the outlet temperature? Because if you have this thing, which is like slightly gentle breeze here, then you can just, yeah, point this thing towards you and you will feel that the cold air is hitting your face. And it can be something like a personal cooler or personal air conditioner, which can give some comfort to the person who is using it, but it will not give a comfort to everyone. So this is basically just a fan, but we have an additional cooling stage in it. But yeah, it will not give you the same effect as an air conditioner, because as I said, the room's temperature will not decrease significantly. So now I turn on this power supply by just pressing this button and we will see what happens. So now you can see that at 1 amperes we have 2.3 volts running through the Peltier cooler, and that's all. So now we just have to wait and see what happens here. The best thing would be to measure directly the heatsink as well, but this is just too crowded now, so we have to rely only on the outlet temperature. So now my idea is to let this run for a few minutes and then I come back and see what happens. And to provide you some information of the time, I will put a watch here and you will see how the time goes. So I try to add the thermocouple and try to squeeze it in between the fins of the heatsink inside this tube. And now it's showing 23.5 degrees Celsius. And if I check the temperatures, then the outlet temperature here, so in this thermometer, is 25 degrees. So it's 0.7 degrees lower than the room temperature, for example, here at this thermometer. So we have a slight increase in cooling performance, but this is nothing, because this unit, which is inside this cooler, has 8 ampere as the maximum current. So what I suggest is that we change this value to 3 amperes and see what happens. So I just go up and wait. So now we are at 3 amperes and 7.3 volts, and let's see what happens. So now I start to have some decrease at the heatsink temperature on the cold side, and I also see that the hot side is now 27.5 degrees Celsius, 27.7 now, so it's going up, and that's what I expect. And the cold side, so this outlet temperature is still 25 degrees, so we have to see what happens in a few minutes. But now you can see that the heatsink itself is getting colder and colder. So I just leave this here for a few minutes and then I will return. So the development of the temperatures slowed down quite significantly within a few minutes. So now we have 19.7, 19.6 degrees Celsius on the fins of the heatsink. Of course, the room temperature is still the same. The outlet temperature here is 24.5 degrees Celsius, so it's 1.5 degrees colder than the room temperature. The outlet temperature of the CPU cooler, which is cooling the hot side, is 31.7 degrees Celsius. And this guy here is again 26 degrees Celsius, which is also the room temperature. So now I go up to 5 amperes and see what happens. So as you can see, 5 amperes and 12.95 volts, 96, changes a little bit. And now we should see some significant change in the temperatures. So now, as you can see, the temperature of the cold side started to drop below 19 degrees Celsius. So this might have some impact on other temperatures as well. So again, let's wait a few minutes and see how the temperatures develop. So after several minutes, you can see that the temperature of this thermometer stuck at around 18.2 degrees Celsius. So it's not really changing, and also the outlet temperature here is not changing either. So I can feel that it's slightly colder than the surrounding air in the room, but it's not a big difference between 24.5 degrees and 26 degrees. So it's just 1.5 degrees difference. And basically this is what I was trying to explain several times, that when you start to apply thermal load, which is in case a continuous feed of the room temperature air on the cold side heatsink, then the thermal load will load the Peltier cooler there so much that you won't be able to keep up with the load sufficiently. So if you compare it with regular compressor-based coolers or air conditioners, then you can see that this is not really a good solution, because there you can really feel and really see that very cold air is coming out, but here you cannot really reach the cold air coming out from the outlet. And this is the problem, that many people don't really recognize this thing, that's just one thing that you are able to cool down the heatsink to a certain cold temperature. But usually you are not blowing air on the heatsink continuously, so it's just stationary air which is surrounding the heatsink in those experiments where people are showing that the heatsink is at -10 degrees, -20 degrees or whatever, but there is no thermal load. And now we have a thermal load as a continuous feed of 26 degrees Celsius air, and in that case it's really difficult for the cold side of the Peltier cooler to keep up with this. And we can see also that the air which is coming out from the hot side here, that is 38.7, so it's quite warm air generated by the hot side of the Peltier cooler. So if I just try to direct this at me, yeah, I can feel that it's let's say pleasant breeze, but it's not that significant. And due to the length of the hose and the weakness of that thing, we are not even pushing too much air through the system, so the pressure here, or the strength of the air which is coming out from the outlet right here, is not that strong. So if you wanted to upgrade this fan to a stronger fan, then the air fed to the cold side heatsink would be even more higher amount. That would mean that the cold side would have even more difficult time to keep up with the air going in. So what I try to say is that you have quite a weak airflow here at the outlet, and even with this weak airflow you are not really able to cool this down, and that's not so good. So I will try to decrease the current because the power supply turned on its cooling. So let's go down to 4 amperes and see what happens. 39 degrees Celsius on the outlet of the CPU cooler. I try to grab these heat pipes. They are warm, but it's okay. Maybe the airflow there could be improved, and that could improve our cold side temperature a little bit, but not by too much. Here the temperature of the outlet air is still 24.5 degrees Celsius, so nothing changed there. The room temperature is still 26 degrees Celsius, so that hasn't changed either, and basically that's all. So as you can see, I separated the hot and cold side nicely, or more or less nicely, and the hot air is getting to another spot of this room, so that's why you could not see any change in the room temperature. There was no increase because the hot air is not coming here, and then the cold air is here. But you can see that despite the fact that I was using the 8 ampere unit, which could provide us roughly 80 watts of cooling power, this was not enough to cool down the air by a significant amount. What I could try is I could try to turn off this fan, because maybe once if I cool down the heatsink to some temperature, it's more easy for the Peltier cooler to keep it nearby that temperature than to try bring it down while I'm loading it. So now what I will do is that I just simply remove the power supply of the fan here and see what happens. So the fan there is back, and now the cold side is increasing because the ampere is just 1 ampere, the current is just 1 ampere. So I go back to 4 ampere step by step. So now I can see that the outlet temperature is also rising a little bit, so 24.7 degrees Celsius. So now you can see the decrease. It's going quite quickly because I'm not feeding the room temperature air to the heatsink. So then the Peltier cooler can cool down the aluminum much faster, and I guess we will reach much lower temperatures there. So you see, we already passed the temperature which was achieved when I was running at 5 amperes, and now I'm running only at 2 amperes, and now we are at 16.7 degrees Celsius. So now you can see it very nicely. This is what I'm talking about, and people cannot understand it, that if you don't have any kind of thermal load like now, because then this is basically just surrounded by this air pocket which is not moving, so it's more or less insulated from this big environment here on the table. So if you don't have the thermal load, then you don't need so much power to cool down the cold side to relatively low temperatures. But once you turn on the fan and introduce fresh warm air to the heatsink, and you do this in a continuous manner, so you just continuously running the fan, then the cold side, or the heatsink attached to the cold side, will not be able to reach this kind of temperature. So now we are approaching 12 degrees Celsius. That means that 6 degrees below the temperature which we were able to reach when the power supply was at 5 amps. And now you will see that if I go and I set the current to, let's say, 4 amperes, I'm pretty sure that we will see negative temperatures on the cold side. And now also the hot side temperature is only 30 degrees, 29.7, and the room temperature is 26. So we are just 4 degrees above the room temperature on the hot side. So that's pretty nice. So now I increase the current to 3 amps and give some help to the cold side. So now you will see some increased rate of cooling. So now we are 10 degrees below the temperature that we were able to reach at 5 amps when the fan was running here. And the temperature of the hot side is still 29.7 degrees. So the CPU cooler can catch up with the temperature very nicely. But now there is not much heat flowing from the cold side to the hot side. So therefore, that's why it is a bit colder than usual. One part is that the current is lower, but the other part is that heat is not really transferred from the cold side to the hot side, as compared to the case when I turn on the fan. So we are approaching 0 degrees now, as you can see. So we are almost at -1 degree Celsius on the heatsink. So this is very cold, and we are only at 4 amps. But in the moment I turn on the fan, this will go up to near room temperature quite quickly. So let's make some readings. So the room temperature based on this is 25.7. The outlet temperature there is 31.7. The temperature here is 26.0, and now this also went back to 26.0. And the temperature on this, which is inside this tube, is 25.5. So now I just try to bend this cable and attach it to the negative side. So now we are at -3 degrees. So let's see what happens if I turn on the fan. So you can see the air is moving. You can see that we passed +10 degrees now. The outlet temperature here is 24.7 degrees. The cold side is now 15 degrees almost. The hot side outlet temperature is 32.7 degrees Celsius. Now it's 33.0 on the outlet there, because it's getting warmer, because now it's more heat, which is the cooling power part, is getting transferred, because I haven't changed the power supply, which means that the P, so the I times U, is the same, but then we added the Q term, which is the heat transferred from the cold side to the hot side, and that apparently warms up the hot side as well. And now that's what you see now, 33.5 degrees on the outlet. And I haven't done anything, I just started the fan. But of course that introduced the heat on the cold side. And now the outlet temperature here is 24.2 degrees. So basically it's just 2 degrees below room temperature, which is nothing. So now 34 degrees there. So that indicates again that we started to transfer heat from one side, which is the cold side, to the other side, which is the hot side. So just to finalize this video and maybe to finalize this topic is that, as you can see, I was using an 8 ampere unit running at 50% of its performance, and I was not able to decrease the temperature here on the outlet by not even 2 degrees, 1.8 degrees only, because you can see that as soon as I turn on the fan and start to introduce hot air or warm air on the cold side, which means that we started to introduce heat load or thermal load on the cold side, then everything just falls apart. And despite the fact that we have quite good cooling here, because the hot side temperature is still only 34.7 degrees Celsius, but despite the fact that this is a good cooling, the Peltier cooler just not capable of catching up with the air here. And let's say you have one unit and that drops down 2 degrees Celsius, then you will need several units to have some noticeable change on the cold side temperature. Let's say you want to drop down 10 degrees, depending on the temperature and everything, depending on the inlet temperature here, room temperature, ambient temperature, so on, then you will need, let's say, 5 units of this, because you cannot run this on the maximum power, of course, because if you run it on the maximum power, then the Joule effect will be so high that only because of the Joule effect, in this case, in the 8 ampere unit, you will have to be able to get rid of 140 watts, and that's a huge amount of power, and you will not be able to dissipate that power with the CPU cooler. And that's just one unit, and that's the problem. So whatever you try to do, you will not really be able to make a proper air conditioner, not even like this kind of thing, because you could see that, yeah, the heatsink without any kind of fan running around it and introducing fresh air could go down to -3 degrees without any problems, even with quite low currents and quite low power. But as soon as you introduce the thermal load, which is the fresh air touching the heatsink, then everything just destroyed. So I hope that this demonstration was instructive and helpful, and you will not waste your nice Peltier coolers on trying building some air conditioners, because it's not really possible. I mean, it's possible in that sense that if you have a lot of power supplies, if you have a sufficient cooling and so on, then you will be able to make one. So it's not impossible, but it's not feasible. It's not a viable solution. I mean, just think about it. If this was a viable solution, then companies would already manufacture these things in large scales, but it's not the case, and this is why. Because the Peltier-based cooling is far away from the compressor-based cooling, and Peltier cooling is good. It has its own small area where it's much better than other coolers, but in this case compressor-based cooling is the only way, because with this thing you cannot really cool down not even a small environment like here, so it's pretty much useless. So yeah, if you see some videos where they try to claim that they built an air conditioner based on a Peltier cooler, those videos are fake, nothing else, because it's just not viable. It's not, and usually they use much worse cooling on the hot side, and usually they use smaller units than this, and they just use some random power supplies and stuff like that, and that will not work. So this is just fake. So this is also some kind of debunking video that you cannot really build a good air conditioner, or not even a bad air conditioner, out of one single Peltier unit, which is the case. So there are dozens of videos where they have like millions of views by building Peltier coolers, and they don't even explain anything, they don't even measure anything, and then they just put one Peltier cooler there and they say that this is an air conditioner, but this is fake. So don't believe those things, and don't waste your resources and good equipment on these kind of things, because you will fail. If you don't believe me, then just build it yourself, and you will see that it will not work. It doesn't work here, it will not work on the other side of the world either. So yeah, but if you like to play some experiments, then it's up to you. Happy experimenting, but I want to spare you from some extra efforts by showing this, so you will see that it will not work nicely. But I have another idea, so I will remove this thing from these hoses and tubes or whatever it's called, and I will put this cold side in a box. I bought a plastic box, and I want to see some other things with this cooler where I think that it will be more useful. So in the next video I will try another type of cooling with Peltier coolers. So stay tuned, please don't forget to subscribe, and we will see each other in the next video.